Great, thank you. Hi, everyone. I'm Alexa Van Eaton. I'm filling in for Paul Jarvis, who just had a baby a couple days ago, so he is otherwise occupied tonight. And I was going to be attending this seminar, so happy to be here and help fill in for Paul while he's doing bigger and better things. Today we have a really cool lineup, and just to kick things off in terms of the seminar series that the Tephra Hazard Modeling Commission leaders have started. This is the second of these new quarterly seminars with 2 speakers each. The plan is that each speaker has 15 to 20 minutes. We'll have questions after, and of course, keep your questions rolling in the chat as they arise. And then at the end, we'll be able to have a chat about what people would like to see in the Tephra Hazard Modeling Commission in the future. The other goals here, of course, are to have early career researchers and scientists from traditionally underrepresented groups. Paul and Thomas have created QR codes on these slides, so you can click if you want to register your interest for giving a seminar or nominating someone that you think would be really fun to speak. Today we have 2 speakers. Our first speaker is Fukashi Maeno at University of Tokyo in Japan, and then Hannah Moore, PhD student at the University of Tasmania. And Fukashi, if you'd like to queue up your slides. Dr. Fukashi Maeno is a physical volcanologist, currently an associate professor at the Earthquake Research Institute at the University of Tokyo. He's an expert on ejecta transport and tephra deposition from explosive eruptions, also magma ascent processes controlling the diversity of eruption styles. And today he's telling us what he's learned from active mafic eruptions in Japan. So let me stop sharing so that Fukashi can queue up his slides.
Okay, can you hear me?
Yes, you sound good.
Sorry.
Just a reminder for those joining, feel free to keep your questions going in the chat and we'll address them after each speaker.
Can I start?
Take it away, Fukashi.
Okay, so yeah, hello. I'm Fukashi Maeno. So I'm very happy to give a presentation here. I would like to thank Alexa, Thomas, Alastair, and Paul and Ellie for organizing this online seminar. So today I will give a talk about abrupt changes in eruption style in large-scale eruptions of mafic volcanoes. So this is a brief introduction of myself. So as introduced by Alexa, my specialty is physical volcanology. So in fact, my targets are a wide range from on-land volcanoes to submarine volcanoes, and from small-scale phreatic eruptions to large-scale caldera-forming eruptions. I will do field work, but also do laboratory analysis. And my recent research topic is listed here, but my talk today will be more about the study of explosive eruptions based on field observations. So first, what is an abrupt change in eruption style? The change in eruption style here refers to the change between explosive and effusive eruptions, as well as changes in eruption intensity, strong or weak. For these changes in eruption style, several important parameters have been proposed as controlling factors. And these 2 diagrams summarize the eruption pattern of mafic volcanoes using magma ascent rate, viscosity, and degree of melt vapor segregation, which are considered important parameters. When the eruption style changes abruptly, these parameters change in very short period. So the main point of today's talk is how changes in magma discharge rates occur and what controls them during the same eruption or series of eruptions. So here we will focus on Izuoshima and Nishinoshima in Japan to discuss this issue. So let me begin with an overview of Izuoshima and Nishinoshima. So Izuoshima is an active basaltic volcano, volcanic island located very close to Tokyo and home to many people. The most recent magmatic eruption occurred in 1986. At this time, the eruption occurred at the summit and flank within about a week. The eruption style was Strombolian in the early phases, which was followed by subpermian eruption in the climactic phase. Lava flows also occurred and resulted in these impressive photos. This eruption led to the evacuation of the entire island due to the flank eruption. On the other hand, Nishinoshima is an uninhabited remote volcanic island about 1,000 kilometers from Tokyo, and recent activity began in 2013, and the island has grown significantly through several active periods and is still active today. So I will focus on the 18th century An-e eruption at Izuoshima and the latest eruption at Nishinoshima. So here the timelines of these eruptions are indicated. The An-e eruption is divided into two major phases. The main eruption phase, which lasted more than 1 year, and the ash phase after ash phase, which lasted 9 years after dormant phase. The main focus is on the main eruptive phase, which has continued with lava flows and explosions during the year. Actually, people were already living on this island at the time of this eruption, so historical records are available to help reconstruct the eruption. For Nishinoshima, the latest eruption began in 2013, which was followed by continuous or intermittent eruptions. But in the latest episode 4, in 2020, the eruptions became very explosive. So these figures summarize the eruption history of Izuoshima and the An-e eruption. On the left side, the magma discharge step diagram is shown. This indicates that large eruptions have occurred on Izuoshima Island every 100 to 200 years over the past 2,000 years. The An-e eruption was the most recent major eruption, and which was followed by a medium or small-sized eruptions, and the latest magmatic eruption occurred in 1986. And the right figure shows the distribution of tephra and lava from this An-e eruption. So my PhD student, Yuya Ikenaga, has revealed a more precise picture of this eruption by examination of the eruptive deposit in detail. So this topic is largely based on his recent work. These photos show an overview of the eruptive products from the main eruption phase of the An-e eruption. You can see that the stratified, well-sorted typical fallout deposits are preserved well. These thick deposits can be divided into several units reflecting several eruption stages. In the left photo, you can see the 1986 deposit at the same distance on the distribution axis of the tephra. So we can say that the magnitude of the An eruption was very large. The fallout deposits during the main eruptive phase are divided into units A, B, and C. As shown here, the distribution of each unit is somewhat different. And the tephra thinning trend is also shown here and compared with other major eruptions. So they are based on this comparison, units A to C all exhibit the characteristics of subpermian eruptions. They are also classified as subpermian by the Piles classification using grain size data. And the results of the estimation of tephra volume and plume height based on tephra thickness and maximum grain size are shown here. The results may vary depending on the method used, but basically they indicate that units A and C were of similar size and unit B was a slightly weaker eruption. As can be seen from the tephra distribution, it is very important to consider the effect of wind in the estimation of plume height in this case. And we further examined the chemical composition of these tephras and found some interesting results. From unit A to C, the chemical compositions change systematically. It is indicated by changes in the amount of Al2O3, which corresponds to the changes in the amount of plagioclase phenocryst. As shown here, unit C is quite rich in plagioclase, and this trend continues to the higher units. Also, in unit A, the chemical composition changes at the stratigraphic level with increasing grain size. This indicates that the chemical composition also corresponds to the eruption intensity. Based on our survey and analysis, we reconstructed the 18th century eruption of Izoshima. And this figure shows the summary of the sequence of the An eruption and its magma system. Based on the stratigraphic relationship and by organizing the timing of the formation of eruptive deposits, we can say that unit C was formed after a long activity involving unit A formation. In other words, unit A was formed in a very short period by a sudden explosive eruption after the unit A eruption. So based on the stratigraphic relationship with the lava flow, the date of the climactic phase is estimated to be November 1778. In addition, based on the feature of stepwise increase in plagioclase phenocryst, we can propose the possibility that multiple magma reservoirs were involved, rather than assuming that all of these events occurred from a single magma reservoir. So actually, this feature is also common for some of other large-scale eruptions in Izoshima, although I don't talk about it today. So our results suggest that initially weak activity may suddenly intensify due to the supply of new magma during large-scale eruptions at Izoshima volcano. So next is the recent activity on Nishinoshima. These figures show the changes in the activity and the topography of Nishinoshima since the beginning of the recent eruptions in 2013. Initially, there was a small old island, but a new island began to grow nearby, eventually covering the old one and creating a new island, 2 kilometers in diameter. The activity was basically moderate and characterized by lava flows and the formation of a pyroclastic cone like this. However, in 2020, the activity became very explosive and the topography was dramatically changed. This diagram summarizes the growth of Nishinoshima based on remote observations, the area and the height, the volume of the island, and the magma discharge rate. Based on these data, we can say that the island first grew on a large scale in episode 1, and then the growth rate decreased. However, in episode 4, the most vigorous eruption to date occurred in a short period, and the island grew again at once. This dramatic change in eruption style is well reflected in the eruptive products. The rock of Nishinoshima are generally homogeneous crystal poor andesite like this, but between episodes 1 and 3, the chemical composition changes gradually with time like this. And in episode 4, some phenocrysts, such as also pyroxene, disappeared, and there were significant changes, such as an increase in plagioclase with high anosite content and the occurrence of olivine phenocryst. In addition, not only large gaps in major elements, but there are also changes in trace element concentration ratios. This suggests that there are different magma has ascended in the recent eruption. And these figures show the results of tracking the sequence of episode 4 based on satellite observations. This figure shows a rapid increase in thermal anomaly in early June 2020. Corresponding changes in topography and diffusion rate are shown here. And this figure shows a change in SO2, which shows that the amount of gas emissions greatly increased in June 2020. And these photos show the eruption captured by JMA, Japan Meteorological Agency research vessel, when it sailed near the island in early July 2020. So this activity was interpreted as no longer Strombolian, but violent Strombolian, and the various observations support the idea that the eruption style has changed dramatically at this point. So we will look at a little more closely at the change in whole rock chemical compositions for the entire activity since 2013. We thought that there should be a mafic end member component that was changing the chemical composition during episode 1 to 3, and that the mafic magma would come to an extension of this compositional trend. But actually, the episode 4 magma has a little different characteristics. So this means that the episode 4 magma was not simply an end member component of the early episode magma, but it was entirely new magma. So based on the results so far, these figures summarize what kind of magma system is spreading beneath Nishinoshima Island. The left side shows up to episode 3, which indicates that lava flows dominated activity occurred due to the involvement of shallow and deep magma reservoirs. And the right side shows that in episode 4, new magma ascended from a deeper level, which was not part of the previous activity. And the deeper magma was rich in volatile components and ascended in a very short time scale without much degassing or cooling, which would have made the eruption explosive and large scale. The depth of magma reservoir is probably 4 to 8 kilometers based on petrology, but further deeper parts are not well constrained. So from this result, we would like to say that there are multiple magma reservoirs from shallow to deep portions, and that they are interrelated to control the explosiveness at the surface. So we have studied the large-scale eruptions of two mafic volcanoes in Japan, and a comparison of these eruptions reveals some similarities. This table shows the results of the comparison. First, eruptive activity can be roughly divided into 3 periods. Period 1 is the stage of intermittent or continuous lava flow and occasional strong eruptions. At Izoshima, this stage lasted about 1 year, and at Nishinoshima, it lasted about 5 years. The period 2 is characterized by the highest magma discharge rate and most intense eruption in the series, which would have lasted about a week in Izoshima and about a month in Nishinoshima. Then there is the decline period after the main eruption, which is an activity that lasts as long as a year. So there may be several cases regarding the magma system corresponding to each activity as indicated here. So actually, we know other volcanoes have similar features as in Piton de la Fournaise and the Yakiatori volcanoes, which are located in ridges or hotspots. So finally, a summary. So there are cases of sudden changes in eruption style in activities caused by mafic magma. Large-scale eruptions at Izoshima and Nishinoshima have something in common. Intermittent and weak activity on a yearly basis is followed by explosive activity with a high eruption rate by magma that is different from the previous one. And one of the causes of the abrupt change in eruption style may be related to the structure of the magma supply system, which is characteristic of mafic magma, as proposed as a set of sill or dike systems. This may be like a depiction of sweet potatoes connected by vines that dug up one after another like this. A similar view is proposed for rich or hotspot volcanoes, but it may be more common even in island arc volcanoes. A similar magma system is developed like Izoshima and Nishinoshima. In the case of prolonged activity with large eruption size, tracking changes in magma composition is very important, but it will be also very important to identify possible changes in eruption style by monitoring hypocenter distribution shifts and ground deformation sources. Okay, that's all. Thank you very much.
We have some questions and comments in the chat. Jeff, do you just want to open your mic and go ahead and ask your question since it's so long?
Yes, okay. Sorry for the long question. Thanks, Fukashi. That was really interesting. My question is around the the mafic component seemed to come after both of the eruptions you described. And I wondered if there was some evidence of mafic injections into the magmatic system prior to the more evolved eruption phases, before the more mafic eruptions took place. And that may be evidenced by magnesium-rich rims in the pyroxenes or high anorthite content in the plagioclases.
For Nishinoshima volcano, actually we have evidences of interaction between shallow and deep magma reservoir, but only limited to these reservoirs. No evidence for further deeper magma reservoir. So, but in episode 4, we can have petrological evidence of the involvement of deep magma reservoir, like occurrence of olivine phenocryst and higher anorthite content plagioclase, but no evidence before episode 4. So we thought that the eruption of episode 4 was triggered by the injection of new magma, or otherwise the evacuation of shallow part might trigger the ascent of further deeper magma reservoir, but it is difficult to constrain which was the first. But anyway, no evidence of the interaction before episode 4. Is it okay?
Yeah, thank you.
Thank you.
You're muted.
Thank you. Fukashi, you showed the images from JMA showing the transition from strombolian to violent strombolian activity.
Yes.
Were the deposits sufficiently preserved on the island to look at the characteristics of the deposits from those different phases, or was the island just too small?
That is very important. Actually, after this eruption, we have no chance. We couldn't get the chance to land the island. So actually, we can see a thick tephra deposit on the lava flows. The deposit is from the most intense eruption, a violent strombolian eruption. But now we cannot analyze the deposit detail. So JMA said this eruption was violent strombolian eruption, but it is not depend on the deposit feature, just phenomena and eruption plume height and rapid cone formation. So
the deposit might be there, but hard to get to.
Yeah, currently we cannot get the deposit. So, yeah.
I had another question, but I wanted to give people a chance to chime in if you'd like to. So feel free to raise your hand or just drop something in the chat or just unmute.
You can't unmute. I have to unmute you. So if you want to, sorry.
Thank you for clarifying that. So if you have a question, please use your digital emoji hand. In the meantime, Fukashi, I wondered for the historic eruption on Izu Oshima.
Yes.
That is really cool. That it sounds like you were able to piece together the written accounts. Were they primarily written accounts from the 1770s of the eruptive activity? And so were you matching the written accounts with the stratigraphy to try to put timing on the scale of months to weeks to each of these units?
Yes, actually, we have historical documents describing these large-scale eruptions, and especially the timing of lava flows can be precisely determined by historical documents. So here, L1, L2, the timing of these lava flows are based on historical documents. So, but other parts, the only mentioning something happened, the explosion occurred for this orange colored part. But we can constrain the timing of lava flows, and we can get the relationship between lava flows and the tephra deposit in the field, so we can precisely determine the timing of unit. So here, other lava flows are not shown, but this unit C, it can be constrained by the timing of lava flows and other evidence of other evidences from historical documents.
In your paper, did you publish or would it be possible to find anywhere the accounts, translated accounts of how people described this eruptive activity? I think there would be a lot of interest in that, how people in the 1770s described what they were seeing.
Yes, yeah, we have Japanese documents, and yeah, it is published in Japanese. So, but we can see what happened in this eruption in detail. There are many records in the documents. So not only this big eruption, but also for other large-scale eruptions, we can get some historical data describing the eruption sequence.
Jeff had another question. I can read it for you this time, Jeff, unless you want to chime in. One more question. You have a clear separation of magma reservoirs in your conceptual models, but could they not be one large distributed system, i.e. a transcrustal reservoir?
I think it is a question for Izo-Shima volcano, but so,
Jeff, are you talking about the one on the screen or for the more recent eruptive activity from Nishinoshima?
Yeah, so the previous conceptual model you showed, you had a clear separation, and I wondered whether or not that's something we sometimes invoke, but maybe it's just part of one big system that different components are being tapped at different times. I asked because a reviewer asked me once to explain why I did the same thing. So yeah.
For Izo-Shima volcano or Nishinoshima volcano, or for both?
I think probably both. Yeah.
Both. Yeah. So yeah, actually we have some evidences of trace element concentration ratio. So actually, different magmas must be involved in the eruption. So, for example, as I shown here, so for the case of Nishinoshima eruption, the early phase was characterized by a low concentration ratio like this, but it dramatically changed at the latest phase of the eruption. So how it is important how we can explain this change. But currently we are separating the magma system into shallow and deeper part, but maybe more data about isotope or other trace element. Maybe we can say something about the more detail on the magma system. So we actually we don't have much petrological data. So now we described like this magma system.
Thank you.
Thank you, Fukashi. We better get Hannah up here before we continue too much further. But any other questions? Keep them for the after discussion, because hopefully we'll have a little bit of time. So Hannah Moore is a PhD student at the University of Tasmania. She completed her master's in volcanology at Bristol in 2018. And over the last 3.5 years, she's been focusing on the 1886 basaltic Plinian eruption of Tarawera, conducting fieldwork and lab work to understand the shallow conduit and vent dynamics of this eruption. And her research is moving into plume modeling, which is what she's going to be telling us about today. Thank you, Hannah. Take it away.
Thanks, Alexa. And it's interesting that you were just talking about historical documents, because that's something that we've also been using for the case of the Tarawera eruption to understand the time constraints of the eruption. So it's a good link into this study. So thanks everyone for attending, and thank you to the IAVCEI Commission for Tephra hazard modeling for inviting me to speak. So this study that I'm about to introduce came out of a curiosity of how multiple vents contributing to a single Plinian plume can affect the sedimentation dynamics and therefore the dispersal of the deposits. So for this project, I'm collaborating with physical volcanologist Paul Jarvis from GNS Science, New Zealand, and my supervisor, Associate Professor Rebecca Carey at the University of Tasmania. So this project is very much a work in progress, and it's my first time developing a numerical model. So I'm really looking forward to sharing my work so far. So why are we modeling a plume with multiple vent sources? Well, eruption plume models have always assumed a single vent source, and this is reflecting the most common case in nature. Most eruptions come from a single source, or sometimes fissures when you've got a low intensity basaltic eruption. However, there's plenty of evidence that suggests that there are some eruption plumes that are fed by multiple vent sources. And for example, the 1886 basaltic Plinian eruption at Mount Tarawera involved up to 4 high-intensity vents, which contributed to 1 Plinian plume. And it's unknown how having multiple vent sources can affect the sedimentation and dispersal pattern. So understanding how multiple vent sources impact eruption plumes and their resulting deposits is really important for improving volcanic hazard assessments and also risk mitigation strategies, mostly in areas with potentially active basaltic centers, which are capable of displaying linear structural controls, such as in the topovolcanic zone, which I will talk about now. So Mount Tarawera is located in the Okataina Volcanic Center, which is the most recently active of 7 major silicic eruptive centers in the topovolcanic zone, which is shown here. And the formation of the Okataina Volcanic Center has been significantly influenced by the regional fault pattern associated with the TVZ. And the topovolcanic zone is an active rifted arc, and this developed in response to the subduction of the Pacific Plate beneath the North Island of New Zealand. And the topovolcanic zone is currently undergoing extension in a northeast-southwest direction, and this is causing transtensional crustal thinning, and consequentially, there's a lot of rift faulting going on. And this linear structural control is reflected in the volcanic activity in the topovolcanic zone, and particularly in the Okataina volcanic center, where volcanic centers have multiple vents in alignment here. And this is in alignment with the rifting axis. And this here is the location of Mount Tarawera. The 1886 eruption of Tarawera is one of the only basaltic Plinian eruptions on Earth with quantitative constraints on the timing. As I said before, we've got some eyewitness accounts from visual observations during the eruption. So if we pay close attention to the map, I will just quickly go through the eruption timing. So on June the 10th, 1886, the eruption began at 1:30 a.m. from a vent within the Wahanga Dome. And this is in the northeastern portion of Mount Tarawera. And these domes here are pre-existing rhyolite domes from the 1315 Kaharoa eruption. Following this, the fissure then opened up or unzipped from the northeast to the southwest. And by 2:30 in the morning, there was an 8-kilometer long line of craters, which were hosting, they hosted erupting vents along the Mount Tarawera segment. And by 3:30 in the morning, the fissure propagated to the southwest. And down in the southwest is the Rotomahana geothermal system. And the interaction of the magma with this geothermal system produced an eruption column, and this deposited wet fall and surge deposits, and these are called the Rotomahana mud. The Plinian plume was primarily fed by 4 aligned high-intensity vents, so these stars shown here, and there were also numerous separate vents erupting at lower intensities along the same fissure at the same time. So the total fissure length is 17 kilometers. Basaltic magma was explosively erupted from about 50 discrete vents, and this was over a period of about 4 hours, so pretty short amount of time. And the eruption column is estimated to have been about 28 kilometers high. On the right is a painting of the eruption, probably produced a few years after the eruption itself, but it's based on eyewitness accounts, and it shows some really interesting features. So, for example, the painting shows that at some point in time, there were actually 4 sources along the fissure which contributed to the eruption plume. And this is backed up by dispersal measurements done in the field by previous authors, Sable et al. And you can see the Rotomahana wet plume going on in the southwest here as well. So here's a representative section showing what the proximal deposits generally look like. So this is within one of the craters. This is the crater wall. So the initial phase of the eruption, which is this really small unit down here, and this was interpreted in the past to have been phreatomagmatic. And then immediately on top is this thick unit 2-3, and this represents a sustained Plinian phase. And there's various dispersals going on within this unit. And the uppermost part is unit 4-5, and this is probably where the eruption switched back to being phreatomagmatic. And the craters were also significantly widened during this phase. So there were tens of vents erupting at the same time along the fissure. There were different vents active at different times over this 4-hour duration of the eruption. And therefore, the contacts between the units are thought to be time transgressive, so they don't represent the same instance in time. We've got some detailed grain size analysis from the proximal environment, which is available to us. So here, for example, there's about 15 grain size samples from one section, from Unit 2-3. And this proximal grain size information is really valuable for our modeling study. It's a really good input for the total grain size distribution. And this helps us to understand the proximal sedimentation processes going on. So what do we aim on doing in this study? Well, we want to first examine the dispersal patterns of the volcanic deposits from the Plinian phase of the eruption, and this was done in the field. We then want to develop a sedimentation model with a vent scenario which best represents the eruption. And finally, we want to determine what the impact of having multiple vents has on the sedimentation processes. So now I'm going to talk about how we're conducting this study. So first of all, to understand the dispersal of the Plinian phase of the eruption, we mapped the thickness of Unit 2-3 in the proximal and medial areas, and we produced isopac maps. We also collected grain size samples so that we could estimate the total grain size distribution. And as I said, this is an input for the model. Next, we sieved each sample to half-phi sizes, and we calculated the total grain size distribution. And finally, we're currently simulating the sedimentation from the plume margin using realistic inputs for Tarawera. And the final step is to compare the results of the model to our field data. This is probably going to be an iterative procedure because well, in order to identify the realistic inputs for Tarawera, I might need to compare the field data and the simulated data to determine which inputs give me the best match. I'm now going to quickly present my field data. So I collected thickness data at 1 kilometer intervals where possible around Tarawera during 2 recent field campaigns. And then I created these isopac maps from the thickness data. So the solid lines that you can see are better constrained than the dashed lines that are a bit further out. So I then produced a square root of area versus thickness plot, and my data is the one in the blue. And I compared this to previous work. And Stable in the data in the green here, they did a proximal study of the thicknesses on the crater walls, whereas the other authors did more distal studies. So one of our aims was to fill in this gap between the proximal and the distal deposits. And you can see we've got about 1 to 3 points in the medial region where there were previously very few points. So for example, only 1 point from Walker and 1 from Puller and Beryl. This region is particularly difficult to get to and to get any kind of thickness data. And this is because it's just outside the crater walls, but it's often too thick to dig through. So now I'm going to introduce the sedimentation model that I'm using. The model is based off a 1D buoyant plume integral model. So integral plume models analyze how eruption source parameters interact with the atmospheric conditions to determine plume characteristics. So despite them looking quite simple, they're actually pretty effective at describing buoyant plumes, and they still remain pretty widely used for things like ash forecasting and decision-making during volcanic events. So the other thing is that this model, or this type of model, is also relatively quick and easy to use, so it's ideal for our kind of study. So that's why we chose a 1D buoyant plume integral model. The sedimentation model simulates the fallout from the margins of the volcanic plume, and it predicts the spatial distribution of the deposit thickness by projecting the areas from the plume margins to the ground, as you can see here. Our model only produces results from the jet and the convective phase, but that's great because that is the area that we're interested in for this study. And this model can account for the effect of wind on both the particle trajectories and the shape of the plume itself. So on the left, we can see this plume isn't affected by the wind, and on the right, both the particle trajectory and the shape of the plume is affected. And the output will look something like this. So we've got a plot of square root of area versus thickness, and this is what we compare to our field data. So the modeling requires quite a lot of initial testing to make sure it's producing realistic results. We'll first select some initial parameter values, and these values we will try to be as realistic as possible with, and we'll set a baseline reference for our future comparisons. And we will then model 3 different vent scenarios. So we've got a single vent, we've got multiple vents, and we've got a fissure. And we'll systematically adjust the variables one at a time and see how they affect the model's behavior. We'll do this for each type of vent scenario. And then we will be comparing our results to the field data and eventually decide which vent scenario best fits the field data. So of course, it's important to note that models like these are simplified versions of reality, and they may not account for certain complexities that happen in reality. So I'll just go through a couple of the assumptions of the model. So mainly, the main thing is that this model assumes a maintained source. This means that the timescale of the mass injection at the source is much longer than the plume rise time. And this is the same for all 1D integral plume models. Secondly, the wind is assumed to maintain the same direction across the height of the plume. However, we know that at Tarawera, the direction of the wind changed throughout the eruption, and the wind direction was also different at different heights. But unfortunately, we can't account for the change in direction. We can account for the difference in wind speed at different heights. So that's good. The next assumption is that the particle trajectories are determined only by the wind and settling velocity, i.e. gravity. And this means that particles with no initial velocity, there are the particles with no, so for example, there's no ballistics included in this model. The particles have no initial velocity. So in order to test the reliability and consistency of the model, we're carrying out some sensitivity analysis. So if the model is well made, changing the number of discrete particle release heights or number of grain size bins will not affect the results. So an example of what I mean by changing the discrete release heights is shown here. So we've got 3 different scenarios. We've got a spacing of 10 meters, 50 meters, and 100 meters for the discrete release heights. So the larger the separation, the quicker the model is to run. So this one will be the quickest to run. And our test results show that provided the number of discrete release heights are large enough, our results are not affected by changing the number of these release heights. And this is the same for the number of grain size bins. And this is just showing that here, all of the different discrete release heights plot on the same line there. So that's great. So what inputs are required for the model? So here we've got a table showing the main variable inputs and the main constant inputs. And these are all pretty realistic values for Tarawera, most of these taken from literature. And it's believed that the main plinium phase was a minimum of 2 hours and a maximum of 3.5 hours. The velocity is estimated by Walker to be 250 to 350 meters per second. The mass eruption rate, there's a couple of studies that have calculated the mass eruption rates, but it seems like there's an average of about 10 to the 8 kilograms per second. And the radius is depending on the velocity and mass eruption rates. And then we've got some constants on the right-hand side. These are the total grain size distribution, which we calculated from our grain size data. And temperature, this was estimated from previous petrological studies. The deposit density, this is from density analysis, and the wind profile is just the average for the month of June, which is when the eruption occurred. So the plume model outputs include things like the plume radius with height, the plume velocity with height, and even mass released with height. So these are just examples of what we get from the plume model. Each color here for this figure showing the mass released versus plume height. These are all the different grain sizes, the grain size, different particle grain sizes. So all this information is interesting, but what we really want to understand is the sedimentation processes. And this is where the model comes in. So as explained before, the sedimentation model simulates fallout from the margins of the volcanic plume, and it predicts the spatial distribution of the deposit thickness by projecting areas from the model, from the plume margins to the ground. So for cases where particles are affected by wind, we need to produce isopachs to visualize the dispersal of the deposit. And this can then be compared to the field data. And then after that, we can calculate the area within each isopach. And this helps us to produce those square root of area versus thickness plots shown before, which is useful for comparison to the field data. So here we've got some preliminary results of the baseline reference for a circular vent. So keep that in mind, it's just a circular vent scenario. And this figure shows the square root of area versus thickness data for both the field data and from our model. So the model data is in here. And I think it's quite nice because it predicts the thickness of the deposits within this difficult to access area where we've got very little field data. And we've got 3 different mass eruption rate scenarios going on here. So although having this data filling in the gap means we can't compare it directly to the results with the field data results, we can say that the model data fills in the gap reasonably well. So we're happy with that. It's also important to note that this vent scenario is not yet realistic. It's currently a circular vent, but we're quite happy thus far with what it's producing. But however, you may have noticed that the plume heights for the mass eruption rate of 10 to the power of 8 kilograms per second, which is probably the most realistic, produces much higher plume heights than what was actually estimated. So it was estimated that the real plume was about 28 kilometers. So 42 is not realistic whatsoever. But this is likely because we're still only testing the results for a circular vent. The next steps are to produce isopachs of the fissure and the multiple vent scenarios. And this code is still being developed, but we expect that the isopachs will look something like these. So from these isopachs, we can produce those square root of area versus thickness plots again, just like we did with the single vent scenario. And we'll then be able to identify which of the vent scenarios best fits our field data and how it has impacted sedimentation processes. So now we've got a bit of context for what's involved in the model. There are a couple more additional limitations and possibly things to consider. So for simplicity, in the case of having multiple vents or the multiple vent scenario, we're going to be keeping the mass eruption rates the same. It's actually not known what the individual mass eruption rates were at each of the 4 vents. And this is pretty much impossible to calculate, but we're going to assume they all had a similar mass eruption rate. The model doesn't consider the effect of lithics. However, the Plinian phase contained quite a low lithic content, and therefore the lithics likely had a near negligible effect on things like the temperature of the plume. We mentioned that the magma interacted with a geothermal system to the south called Rotomahana. The wet plume actually did mix a bit with the dry Plinian plume, and this may have affected the sedimentation dynamics. However, we unfortunately can't account for this effect, so we're going to have to ignore it in this case, but it's something that I'd love to look into in the future. And next, there is the possible effect of the additional mass and heat coming from the lower intensity eruptions that are occurring simultaneously with the higher intensity eruptions. The lower intensity eruptions were, however, likely orders of magnitude smaller than the higher intensity ones. So the effects were potentially negligible, but again, this is something that I'd like to potentially explore in the future with a more complex model. So we hope that in the future, this model can be readily available to model sedimentation dynamics of highly explosive basaltic eruptions. The different vent scenarios in this model will be useful for modeling other highly explosive basaltic eruptions with linear structural controls, such as others in the topovolcanic zone. And this model may be further developed to model the sedimentation from silicic plumes, which are the other types of eruptions in the topovolcanic zone. And so we can adjust parameters like the ones on the screen, deposit density, total grain size distribution, etc. But there's a few more complexities associated with these silicic plumes, such as the aggregation of finer particles. So I will hopefully be publishing this work in the future, so keep an eye out for that. But I just wanted to say thank you for listening, and I hope you enjoyed. And again, this is an ongoing project, so I really appreciate the opportunity to share and perhaps receive some constructive feedback. So thank you very much.
Great talk, Hannah. Great project.
Thank you.
Sure, there are lots of questions. I've been blowing up the chat in the meantime. Let me start with just one of these. And I'll note that we are at time now, but we'll try to be efficient and move things along while still getting in questions as they show up. Gosh, it's a challenging modeling problem, right? Because you're tempted to just maybe use a large source, but in a 1D plume model that would create an unstable column. So you need to have the high intensity, high velocity components of this large sort of dispersed source area. So in your, I guess my question is, in your experiment so far, have you got a sense of how having such a large area would affect the overall plume height? You know, because you're kind of got a large mass eruption rate over a large area, and yet discrete components. So any sense of what that would do to the plume height as observed, you know, if we had remote sensing observations in 1886, which we obviously didn't, but.
Yeah, that's something that I've been thinking about. And I think with this model, we're expecting that when we have multiple vents or a fissure, well, we've got more kind of vent surface area, you might say. And so you probably got like the energy is more dispersed, and therefore the plume height results will probably be lower for those cases than the circular vent. However, as I said before, we don't actually know what the effects would be of the extra heat coming from having more vents and even having those additional lower intensity eruptions occurring at the same time would be, and that could potentially actually boost the plume height. So there's so many complex things that we need to consider when thinking about the plume height, but it's a really great question. Something to think about.
Does anyone else want to chime in? And if so, oh, Jeff has a question. Jeff, unmute.
Yes, okay, sorry. Hi, Hannah. Great talk, by the way.
Thank you.
Yeah, I was wondering, in terms of the modeling complexity, do you assume that each of those 4 high-intensity events were active at exactly the same time? Because any switching on and off would complicate the modeling even further. So I wonder just how, I know that given that that's a complication, how are you, I guess, assuming or dealing with that complexity?
Yeah, so that is an assumption that we've made, but you're right. There is a possibility that those events were kind of occurring in the time transgressive nature of the eruption, so they could have been active at different times. So it's a simplification of the model, but we do like that the painting shows all 4 events being active at the same time. That is a nice piece of evidence. But yeah, it's true that they might not all be occurring at the same time, but hopefully the deposit dispersal or deposit pattern will appear somewhat similar to if they weren't occurring all at the same time, if you know what I mean.
No, I get it. And I guess just one very quick subscript here is that I think it's really interesting to try and model the Rotomahana impact on the other plume, because just in general, I don't think that there's really been any modeling approaches that have looked at the complexity of adding 2 quite different plumes, or even the interaction between ballistics and plumes to understand that interactive behavior. So I think this is a really tough problem that you're trying to deal with, but
Yeah.
I wish you well.
Totally, that Rotomahana mud is a pain, because there could be all sorts of other processes happening, like sticking to the scoria and making it fall out early, and all sorts of plume mixing phenomena happening that we don't fully understand yet. So definitely a complex topic.
Hannah, we have another question in the chat, a comment and a question. The question part of this is, do you assume terminal velocity for the particles once they start settling from the plume?
Great question. Technical modeling question. I think that's an assumption, but I'm not entirely sure, so I don't want to answer that one. I'm afraid that's something for me to check with the model itself.
Defer for later. And it sounds like there could be some research overlap there, so maybe worth getting in touch anyway.
Definitely. Yeah, sounds good. We'd be keen to get in touch.
Any follow-up questions or comments? Okay. Thank you so much, Hannah. That was great.
Thank you very much.
Let me share screen again for this last part of this slide that Paul put together regarding reminders on how to get involved with the commission. These very nice QR codes, obviously subscribing to the mailing list. You're all already subscribed, but they're here for future notice. Some of the things that are worth bringing up here are any general thoughts on what people would like to see out of the commission, especially considering there are upcoming meetings. Thomas Aubrey has mentioned that there are some potential discussions in the works for a field workshop at IAVCEI 2025, which is of course in Geneva, but there will be Italian field trips in the works. And so I think there's a lot of scope available for people to contribute ideas for what could be tackled in a field-focused workshop. I don't know if anyone wants to comment on that. For some reason, I can't see the participants anymore.
I can see them, so I can't see anyone else at the moment.
Yeah, feel free. I think do people have to raise their hand if they want to be unmuted?
Yeah.
Okay, so if you want to make a comment, you have to you have to raise your hand so that Ari can unmute you. Oh, Jeff, you said session proposals for IAVCEI too. Yeah, I think that's going to be key. People proposing Tephra related sessions. But I'm personally excited about the prospect of a field workshop where we could get together to test certain measurement techniques and potentially some of the evolving checklists that people are developing in terms of types of observations to look for in the field for early career researchers who, are getting out there to look at deposits in a new area or in a new type of eruption style, looking for characteristics like aggregation and different deposit textures. So that could certainly be something to test. Another thing is that there is a working group on grain size measurement techniques. And so coming up in the next couple of months, we're going to be sending out an email to the Volcano listserv and of course to the commission participants for anybody who's interested in contributing measurements of grain size from volcanic deposits to do an intercomparison of different laboratory techniques and essentially compare results from various methods. Okay, Ari just pointed out that attendees can unmute themselves, so if you have something to add, that should work.
Thank.
Well, to test this idea, someone has to actually unmute themselves. Come now.
Yeah, I'm here.
Yeah, you don't
I was
count,
here.
Jeff, because I already unmuted you before.
Sorry.
Yeah, no, go ahead and expound on that, Jeff.
No, it's just in terms of lasers, we do a lot of grain size work, right? And we do a lot of sieving, and then we often laser size the pan fraction, right? Which might be, I don't know, 4 or 5, whatever. But various people do it in various different ways, and I'm kind of surprised that there isn't a really robust way of doing it and actually testing to see what's the most statistically robust way. So it's my little 2 cents.
Yeah, and the other thing is that laser diffraction is kind of old news now. Most labs are using dynamic image analysis and all kinds of new techniques that are shiny and expensive, and we don't really have a good sense of what types of uncertainties these different methods are bringing to bear on the total deposit results.
And actually, that's one thing we've been talking about here for a little bit of time, but using distrometers, so these precipitation measurement devices, which helps you measure dynamically the grain size distribution of particles falling out of a plume. So I think the combination of all of those kind of lab-based, field-based, both the deposit and active deposition and the modeling would be amazing if we could somehow use this commission to come up with more, not necessarily consensus, but ways in which we could get better data from results.
Yeah, I mean, step one would be to get results from different labs and just look at just compare the results, see how comparable the results are. Hannah just showed a thickness versus square root of area plot for the same deposit using different methods, and there were different slopes for the distal aspects of the deposit. So just even getting different grain size results from different labs for the same sample would be very interesting. And then we could progress to thinking about, okay, what would be a best practice or a gold standard or something, without necessarily imposing standards, but having something out there. I mean, Hannah, you've been doing grain size analysis. As an early career researcher in this field, how's your vibe on how easy it is to find documentation for grain size analysis of volcanic deposits?
I don't know if I'm the best person to ask because I'm just using the Tarawera grain size that's that's really available to me because my supervisor has all that stuff. But I can imagine I don't know where I would look. If there's like a database somewhere, potentially, I actually don't know. Do we know of that?
It would be great to have more database. There's not a huge, so the previous leadership of the Commission on Tephra Hazard Modeling. Oh, someone's got their hand up. I can't see who that is though. Oh, Eleni, can you unmute yourself? Hi.
Can you hear me?
Yes. Can we see
good.
you?
No, sorry, I don't have a webcam connected to this computer
okay.
at the moment. Yeah, sorry, I just wanted to mention. So I'm primarily I'm a PhD student at the University of Hawaii. I'm primarily in planetary science. I do Mars things, but yeah, I have been doing a project for my PhD focused on ash settling on Mars, and I've actually been looking at a lot of the TGSD like data for these TGSD data sets, kind of as like testing for my model. And I just wanted to add, yeah, it's a bit kind of difficult sometimes. There's some good like overview papers that kind of talk about some of the main grain size data sets, but yeah, it is a little bit difficult, and I've kind of been going into the weeds of like supplementary info, and it's not always super standardized, like you said, the measurements and exactly what people actually report. So I think this thing from the planetary science perspective as well is something that would be like really useful. So I just wanted to add that.
Thanks for that. Yeah, that's a really good point. There's fields beyond terrestrial volcanic deposits to consider. Yeah, I mean, even just how to stitch the fines and the coarse measurements together is not straightforward, and everyone seems to have their own method for doing that. So it seems like there's a lot we could address as a group. And yeah, Jeff, like you're saying, if there's something that we could measure in real time, I don't know if that's feasible at Etna necessarily, if we'd be allowed to be there if there was something like that going on, but thinking more broadly, not just historic or preserved deposits, but things that could also be compared with real-time measurements would be a really good idea. Well, unless someone would like to add anything there, I think we can probably end it. We are 18 minutes over. And thanks again to our speakers. Thanks to Paul for pulling this together and getting people to fill in while he's off being a dad. Okay, thanks everyone. Thank you, Hannah and Fukashi.
Thank you.
And Ari.
Thanks for organizing.
Thank you very much.
Thank you, Fukashi.
Thank you.